digital quantum computation on a trapped ion device. At the same time, I'm extremely excited by talks I heard today. For instance, Vadim's talk this morning, where I kind of realized that even though this is about random circuit sampling, which you might think has nothing to do with thermalization, but some of the techniques being used, for instance, out-of-time order correlators and talking about quantum chaos, these are really concepts that we talk about when we study how systems thermalize. So that gives me some hope that perhaps there are more applications that could be useful kind of to understand the way forward, how we can make these quantum computers solve useful problems. All right, how could these problems look like? Here are some examples that basically from high energy nuclear physics, and that is, for instance, how does the matter created in an ultra-relativistic heavy ion collision come to thermal equilibrium, or how did the early universe come to sorry? Anything wrong? Oh, but you heard me before? Okay, maybe I should tone down it a bit. All right, so you all heard me. That's great. But here are two great examples of some of the problems where a quantum computer could be used for addressing these long-standing fundamental problems. And if you don't believe me, here are some examples of simulations, quantum simulations of dynamics of such systems that just came out in the last 2 years. And I think this is a very impressive list demonstrating a lot of progress. Sort of the language behind almost all of these papers that you see here is lattice gauge theories, which of course we know, or gauge theories underlie the fundamental descriptions of nature, but they're a very interdisciplinary language in the sense that I can describe materials that have long-range entanglement using gauge theory formulations, or can use them to make very good Fermi and qubit mapping. And essentially, the way certain classes of quantum error correction work is very intimately tied to kind of the mathematical formulation of quantum error correction. So these are, this is basically the setup. But why thermalization specifically? Why do we care about this? Of course, from a physicist perspective, there are just a bunch of systems out there, not only in high energy nuclear physics, but also systems that I can engineer in a lab that are really challenging to describe theoretically and understand how they come, once I hit them with a hammer, to thermal equilibrium. So here are just some buzzwords that have excited physicists for, well, 40, 50 years almost, starting with quantum chaos, thinking about the eigenstate thermalization hypothesis, which is only 30 years old, but basically which formalizes how an isolated quantum system thermalizes, and then what role entanglement plays. But of course, if you think about it from the quantum information perspective, one thing you might say, why is this interesting? Well, I would say maybe because it's too hard for a classical computer to simulate. I should give you a little disclaimer. First of all, it might not be too hard. I don't know that. And even if I knew that, if I could prove it, I probably couldn't even tell you what that meant. So that's something we might have to talk about. But if you believe me for now that maybe thermalization is an interesting application because it's too hard for a classical computer, then we can immediately talk about things like quantum complexity. What are the quantum resources that make thermalization quantum as opposed to classical? And maybe are these problems because they have additional structure? Is that an interesting kind of handle that I can use to come up with new ideas in benchmarking and verification, for instance? So now you can put your hats on. Of course, if you're a physicist, maybe that's the arena that you find interesting. But if you're a computer scientist, my hope is there's a great overlap. And so this is perhaps an exciting interplay here. All right. So what I want to report on is an experiment we performed on a trapped ion device, since there were 2 trapped ion talks already by Ken and by Eli, and thank you very much for this very nice introduction. I'm not going to tell you more about how a trapped ion quantum computer works, other than it's essentially we use it as a digital machine that has all-to-all connectivity and really excellent fidelity. This is the experimental team here, and on the theory side, Zori Davoudi And we worked with this model here, and if this is my theory slide, if you find this, just think of it as some kind of weird spin model. But what makes this a gauge theory is that there are local constraints, which, if this were electrodynamics, you could think of basically electric field lines must come from charges. That's kind of a local constraint that I have to impose in my theory, and this is, if you wish, the spin version thereof as an operator, okay? So this is the system we simulated, kind of a string or a loop, periodic in plaquettes. Actually, we simulated this, which is a dual version of it. And we were wondering, can we take this model and can we see thermalization and kind of quantum simulate thermalization in this model? Right, so what did we do? Here's our quantum computer. And the qubits of this model that you just seen, we encoded it in these trapped ions. And then it's easy, right? You just basically perform a time evolution circuit. So you start with some initial state, and out comes the thermal state, right? Well, it's actually not that easy for several reasons. Well, first of all, it cannot give you a thermal state because it's unitary evolution. But moreover, for thermalization or to see things that are thermal, very deep circuits are required because I have to take a system, I have to evolve it in time for quite some long time, and this is a digital machine, and we have to do tolerization. So that means basically we have to perform a very deep circuit. That's problem number one. Problem number two is what is it that you actually measure? And we tried to circumvent this problem a little bit. We did the following. We measured random observers. So what we actually were doing is, after we evolved the state for some time, we measured random observables, and what we wanted to learn is something called an entanglement Hamiltonian. Right? What is an entanglement Hamiltonian? An entanglement Hamiltonian is a weird object. It's basically minus the log of a reduced density matrix. So it's just a reparametrization of my state, which for the first time was used in the context of fractional quantum Hall effect materials as sort of a very useful way of kind of encoding the entanglement of a state, but like the entanglement structure, so in a more complicated way other than just saying, well, here's the von Neumann entropy or so. And it's not called a Hamiltonian for no reason. It really often has the structure of a Hamiltonian, and importantly, you can throw random matrix theory at it. Because of that. And random matrix theory is that thing that tells us a lot about quantum chaos, and quantum chaos is, if you wish, a prerequisite for thermalization. So that was basically then our target. Moreover, it turns out that the entanglement Hamiltonian of a quantum state, if I have some information of what physical Hamiltonian kind of evolved that state, is often local. That just turns out to be the case, and so I can parameterize then my unknown state and really try to learn it from an experiment by making these random measurements. And that's basically what we did. And we wanted to find out, basically, if we evolve a system in time, can we learn from its entanglement structure whether it's an integrable model or whether it behaves chaotic and therefore will thermalize. And basically, the vehicle to do so was random matrix theory thrown at the spectrum of these entanglement Hamiltonians, which we measured in an experiment, right? So that's the basic idea. Here are the results. When you measure this entanglement Hamiltonian, you can come up with a quantity that looks a bit funky here, but essentially what it is, you look at the spectrum of the eigenvalues, and you want to know whether they want to be close to each other or whether they repulse each other. So if they want to be close to each other, you see what's in the left panel. If they want to be far from each other, if they repulse each other, they do what's in the right panel. And that's a prediction by random matrix theory. Something that behaves chaotic should look like in the right, and something that's not chaotic should look like in the left. And this is here as a function of time. So there are three time regimes. Of course, at the beginning, the state isn't evolved very far. Chaos hasn't built up. But you see at later time, we see signatures of quantum chaos. You can basically plot where the mean is of this distribution. If it's at 0.4, it's called a Poisson distribution. It's no quantum chaos. But if it's at 0.6, it's called a Gaussian unitary ensemble. And random matrix theory tells you that is quantum chaos. Right. So that's basically it. And you can measure things like the entanglement spectral form factor, which has this famous plateau ramp structure, which we also saw in experiments. So everything that's orange here is data from a digital quantum computer. All right, how much more time do I have?
You've got 3 more minutes to each conclude.
Okay, 3 more minutes. So at the beginning, I tried to argue that there are cool connections from basically more a computer science perspective, and that I really can't prove that simulating thermalization is classically hard, but that I also don't really know what hard means. And why do I not know what hard means? Because it depends on what hat you put on. For instance, if you're a computer scientist, by hard usually means something like Clifford circuits versus not Clifford circuits, right? If you say hard and you say to a physicist, it's can I work this out on a piece of paper or not? So integrable versus non-integrable. So the concepts here is essentially computational complexity on one hand from the QI perspective versus ergodicity, or a system basically not being integrable from the physicist perspective. So could these two things have anything in common? The answer is surprisingly, or maybe not so surprisingly, they have a lot in common. So here's some recent results that came out where this is a very similar model. The details don't matter so much, but here we found basically a so-called quantum many-body scars. And quantum many-body scars are funky eigenstates of a Hamiltonian that is non-integrable and strongly coupled and does everything it should be to thermalize except for these states. And we found these states in this model that also happens to be a lattice gauge theory. And here we show their distillable entanglement, and the red ones, these are the quantum many-body scars. The details don't matter so much. But they live in a subspace that's exactly decoupled from every other state in the Hilbert space that's thermalizing. And the important point here is that this subspace is spanned by stabilizer states. So it's basically a subspace with provable low computational complexity in kind of this resource sense, which simultaneously is also the thing that breaks quantum ergodicity. So these two views, I'm not going to explain this plot, but these two things, computational complexity that a computer scientist would talk about, and ergodicity that a physicist would talk about, for this model, they are the same thing, right? And with that, I'll just jump over my summary so you have some chance to ask a question. Thank you very much for your attention.
Wonderful. Thanks a lot. Questions, please.
Thanks very much for a very nice talk. I just want to see if I'm a bit confused about one thing, which is you looked at sort of thermalization criterion based on kind of level spacing statistics, but for me, like random matrix theory tells you nothing kind of about thermalization scales, because it's probing physics on sort of exponentially long time.
Shorter time scales.
Exactly. Yeah. Whereas thermalization occurs on time scales much quicker than that, like polynomial system size.
Okay, I should have been more precise. So strictly speaking, what we were probing here was not thermalization, but quantum chaos, and which is a prerequisite for thermalization.
Further questions?
How robust are the spectral signatures in this entanglement Hamiltonian to device noise?
Surprisingly robust. So the device has quite some noise. If you look into the paper, you'll see how much, because we also measured in fixed spaces and kind of gave an estimate for this. But essentially, the phenomenon you're looking at is universal, and that's the key point. So we're not even reconstructing or getting the right entanglement Hamiltonian out with our tomography scheme. Actually getting it out precisely would cost us exponential resources. But we get it we get a good approximation. We learn a good approximation that has the correct universal features. And then it's either level repulsion or it's no level repulsion. That's the beauty of random matrix theory.
Further questions? Okay, well, if everybody's still trying to think of a question, I guess I'll have to ask one. So one thing that I'm kind of curious about is if you're assuming random matrix theory and you're inputting a state, for example, that's Haar random, right? With very high probability, I can compute the expectation value of, say, almost any k-local observable that I'm interested in classically. Right. So if you're looking at something like this, why would you expect that taking computing expectation values of arbitrary observables would typically be difficult for chaotic systems?
I think that's exactly the million-dollar question. Two things. Thermalization isn't random because it's not a random circuit. It has a conservation law, which is energy conservation. So that's a subtle difference. But
Thermalization, what do you mean? Because if you're taking a look at, some of these Srednicki results and some of these earlier ones, they all treat them as random states in a higher dimensional Hilbert space.
No, this is an extremely important point, and I don't think anybody has a good answer to this. Thermalization ultimately depends on the observable that you look at, and we have, I don't know, 40, 50 years of experience of, studying thermalization with classical computers. And for some observers, like single body observers, we're doing a pretty good job for a lot of systems computing them classically. So I think but I think there are interesting questions to be asked there still.
We got a question over there.
Question, but a comment on the last question. As you said, if you assume certain properties of Hamiltonian dynamics looks like random, explaining thermalization becomes trivial. So in a sense, eigenstate thermalization hypothesis is kind of trivializing the mechanism of thermalization. It just happens, right? Of course, there are significance behind it, like why such a high complexity arises, and numerically it seems to be true. But I think the real challenge is, why is it okay to assume random being the typical state that arises from the nature? And that's conceptually very difficult to answer.
Yeah, how hard could it possibly be for a quantum computer to build a random state, right?
Yeah, or random state under certain conservation laws.
Sure.
If you throw energy conservation in, chemical potential, right?
And unitary designs and all the rest of it.
Exactly.
But any last question? Okay, if not, let's thank our speaker one more time.